So in this video, I'm going to introduce you to the piece of software, the piece of MATLAB code that we're going to be using to generate k-values for the programs that you'll be writing to solve separations problems this semester. It's relatively straightforward to use, and I'm going to introduce you to the function now, its required inputs, and the format of its output. The name of the key function is get k-values, logically enough. And it takes the following arguments. It takes a pressure, it takes a temperature, it takes a vector corresponding to the numbers of the components that you're going to be getting the k-values for. So get k-values draws k-values from a property database, and each component that is listed in that property database has a corresponding number, and we call that number the component number. And you'll see this in a second. So component number. All right, and then because k-values are functions not just of temperature and pressure, but composition, we also need compositions in the liquid phase and compositions in the vapor phase in order to obtain the k-values for each of these components. So in the liquid phase, we have one composition for each component that we're trying to get a k-value for, and same thing in the vapor phase. Okay, so this is pretty straightforward. Pressure and temperature are scalars, right? Just a simple pressure value and a temperature value. Pressure is in pascals. Right, so you need to get your pressure in units of pascals in order for this to work. That's the only unit it will work with. Temperature is in units of Kelvin. And again, units of Kelvin is the only unit that will work here. Component number is a row vector. Right, so you'll enter it in brackets with whatever your component numbers are. So separate by spaces. Say you want to look at component numbers 1, 2, and 3, and we'll talk about which chemicals these component numbers correspond to in a second. If you want to look at these three components, then you enter a row vector containing the integers 1, 2, and 3. Just have more elements in this row vector if you want to look at more components. And again, these numbers correspond to a database, and we'll look at how you look up which chemical is corresponds to which number in a second. All right. X and Y then are both optional arguments. And they're formatted, if you do choose to use them, in exactly the same format as the row vector that you enter for the component numbers. All right, so you'll enter a composition for each of these components in the x vector and the y vector. Right, and of course these compositions should sum to 1. So again, if you have three components, you'll have a composition of 0.333, for each component in the equimolar case. If it's not equimolar, of course, it's whatever composition is represented by that component in each phase, right? So the first element of the composition vector corresponds to the first element of the component number vector, right? So 0.333 is going to be the composition of component 1 in the liquid phase if we enter this as our x vector. Same thing for the second one and the third one. So 0.333 corresponds to component 2, component 3. If we decide to enter some other order for our component numbers here, like let's say we're looking at component numbers 3, 4, 7, and then we decide we want to look at component number 2, right? These component numbers refer to the database that, again, we're going to be looking at in a second, right? So they refer to the labels for these chemical components in a database. The order of this component number vector is going to define what component we're referring to when we use our composition vectors, and it will also define what k value corresponds to what component when we get the output from this get k values function. All right, so if I enter in my component number vector 3 as the first component, then the first element of the composition vectors, x and y, will also refer to that component number 3, the first component. And when my get k values function outputs the k values, the first element of that output vector is going to refer to this component number 3 because I entered that as the first component in my component number vector. And I just realized that I really didn't bother to spell component here. I hope you get what I was trying to get at there. Okay, so as I said, the x and y vectors are optional. If you enter just one of them, it's going to be treated as the x vector, as the liquid phase compositions. And then the vapor phase compositions will be treated as equimolar. The vapor phase is going to be treated as equimolar if you don't enter anything for y. If you don't enter anything for x or y, both liquid and vapor are going to be treated as equimolar mixtures of whatever components are defined in this component number vector. Okay, so that's really all you need to know. There's also an interactive mode. If you call the get k values function without any arguments, it'll enter in interactive mode and allow you to enter all of the data manually. All right, so let's go to MATLAB now and take a look at an example using this get k values function. Okay, so now we'll take a look at the get k values function. Here we are in MATLAB. I've got the command window open, and I'm in a folder where I have all of the files needed to run the get k value function. I'm going to give you a zip file that contains all of these files. When you unzip it, it'll create a folder, and everything you need to run the function is right here in that folder. Okay. The two pieces of code that you're actually going to access, that you'll run yourself, are this list species function and the main function itself, the get k values function. What list species does is it lists all the all the chemical species in the database, and it gives you the component numbers corresponding to those species. So if I run list species, I get my database. It's not a very big database. There are only 9 components in it right now. The way it works is there's a component number, 1 through 9, and next to that component number there's a corresponding species name. So we have propane, M-butane, I-butane, M-pentane, I-pentane, etc. All right, so these are the numbers that you'll enter into the component number vector when you call the get k values function. And the leading zeros aren't necessary. They're only there so this database can be expanded into 3 digits. So when you enter the component numbers, you only need to enter the integers 1 through 9, depending on what components you're looking at. All right, so let's run get k values now, and let's run it in its interactive mode. So to run in the interactive mode, we just call get k values without any arguments. And you see it tells me enter in interactive mode, and it wants a pressure. So I'll enter the pressure in pascals. Wants a temperature in Kelvin, and now it asks me how many components. In order to make this simple, I'm just going to do 2 components, and let's make these components N-butane and I-butane. So I'll enter the component numbers for N-butane and I-butane. That'll be 2, and it asks me the mole fraction in the liquid phase, and we'll just make this equimolar in both phases, 0.5, and the vapor phase, 0.5. All right, so component number 2 is going to be I-butane, so I look up the number corresponding to that, and it's 3, 0.5, and 0.5. All right, and it gives me an answer, and this answer is a vector with 2 components, with 2 elements, and each element is a k value. All right, so the k value here is 1.8 for the first species that I entered, species number 2 in the database, so that's N-butane. And the second element is the k-value for the second species that I entered. Species number 3 in the database is I-butane, right? Okay, you might notice that this actual situation of k-values does not correspond to the compositions that I entered. It does not correspond to a real equilibrium system. We'll talk about how to get your k-value calculations to converge on a valid equilibrium later. For now, all you need to know is how to go about obtaining actual values for those k-values at given temperature, pressure, and composition. All right, let's take a look at how the k-value function works now in the non-interactive mode when you're calling it with actual arguments. Let's clear this first. And we'll call get k-values. And the arguments are, well, you can see right here, it pops up a helpful reminder for me. The arguments are pressure, temperature, and then a vector corresponding to the component numbers, and this is going to be a row vector. And let's say I want to look at the first 6 component numbers, or component numbers 2 through 7. So let's say 2, 3, 4, 5, 6, 7. All right. Now, in order to know what component numbers those are, I need to look it up in my database. So I would use the list species function to look up my database and to find out which chemical species these component numbers refer to. All right. Now, if I run it without any X composition or Y composition, without any X composition or Y composition vectors as arguments, it's going to assume equimolar compositions in both the liquid and vapor phase. And I can run it. It tells me assuming equimolar composition in vapor and liquid phase, and it gives me the k-values for this system. And as you can see, some k-values are above 1, some k-values are below 1, so we are going to have a vapor-liquid equilibrium in this case. I can also run it without a liquid phase vector. I could also run it with a liquid phase vector, but with no vapor phase vector. And let's just do, say, 0.1, 0.1, 0.1. So that's and make the next one 0.1 as well. So that's a total of 0.4. So the next 2 components correspond to a total of 0.6. So we have 0.3, 0.3. All right, so we have 1, 2, 3, 4, 5, 6 compositions for 1, 2, 3, 4, 5, 6 components. And the first element in this liquid phase composition vector corresponds to the first component, component number 2. And same thing for every subsequent element in the liquid phase composition vector. With a liquid phase composition vector defined but no vapor phase composition vector defined, then it's going to assume equimolar compositions in the vapor phase. And it will tell us that, assuming equimolar composition in the vapor phase, and it will generate the k-values. And you'll notice that the k-values are slightly different when we no longer assume equimolar composition in the liquid phase. Okay, and then finally, we can run it with defined mole fractions in both the vapor and liquid phase. So if we set the vapor phase equal to the liquid phase composition, hit return, we get values for the k-values that are now just a little bit different than they were in the case of equimolar composition in the vapor phase. Now remember, what it's returning here is a k-value for each of the species that we've defined in our component number vector. So the first k-value here, 1.2151, is going to correspond to the species number 2, which again, if we look up by entering the list species function, component number 2 is N-butane. All right, so again, let's look at the output of the k-values. So N-butane, species number 2, as defined in the component number vector, will have a k-value of 1.2151 at these conditions. These conditions being pressure, temperature, and composition in the vapor and liquid phase. That k-value will change as those thermodynamic state variables change. All right, so you'll be able to integrate this get k-values function in any of your code. Again, it's going to be available as a zip file on the Piazza page, and upon unzipping it, you'll have all the code that's necessary. The only programs you'll really run here are the list species program, to get this database and know which species is which when you enter your component number vector, and the get k-values function itself, which outputs k-values at a given temperature, pressure, and composition.